Hello and howdy, ladies and gentlemen. Welcome back to more of the Grade 9 Pascal contest. That is the Grade 9 multiple choice contest put out by the University of Waterloo. We're on the very last question, question 25. So if you want any of the other questions, you can go back on my channel and look at some of the previous videos. I will have put out the other videos. We just did question 24 a little while ago. But now we're on to question number 25, the very last one, and it reads, a palindrome is a positive integer whose digits are the same when read forwards or backwards. For example, 282 is a 4-digit palindrome, so I can read it 2882 or 2882. And 49194 is a 5-digit palindrome, because it reads the same forwards as it does back. There are pairs of 4-digit palindromes whose sum is a 5-digit palindrome. One such pair is 2882 and 9339. How many such pairs are there? Ooh, okay. So, what do palindromes look like? 4-digit and 5-digit palindromes. So, if I'm just looking at a general 4-digit palindrome, so that's going to look like A, B, B, A. It's got to read the same forward as it does backwards. And I also, because it's 4-digit, A can't be 0. So, I like ABBA. ABBA's got good music. ABBA also has a wonderful song called Waterloo, and the University of Waterloo makes up these contests. Isn't math fun? No, so A can't be equal to 0, and we don't really have any restrictions on B. A 5-digit palindrome looks like, well, the first and last have got to be the same, and then these two have got to be the same, and then there's a middle digit, C. And once again, A can't be equal to 0. Okay, so we're just getting a feel for how palindromes look, but A's and B's, they're all single digit. The ABCs are all single digits. Okay. So what we want is all pairs ABBA and CDDC that equal another 5-digit palindrome EFGFE. Okay, that's what we're looking at. And A, C, and E can't be equal to 0. Okay. Well, ABBA. I'm looking at these as just as digits, so I could actually say A times. Well, we're not saying A times anything. We're going to say 1,000 times A. So that's the proper way to write it. Because whenever I have digits specifically written out, I often like to write them as an equation related with the actual place, the thousands, the hundreds, the tens, the digit placement involved here. Okay. Now I can group my A's and say that this is 1001 A plus 110 B. And I can do the same thing with CDDC, and I could do the same thing with EFGFE. So 1001A plus 110B plus 1001C plus 110D is equal to 10,001E plus 1010F plus 100G. Okay. So what does that really get me? Well, I can group the 1001s together. So 1001 A plus C and 110 B plus D is equal to, I'm not going to write out the expansion all over again. I'm just going to write EF GFE again. If I need it, I've got this expansion out here. Okay. So, I was given an example of 2882 and 9339. So that means 101 A plus C plus 110 B plus D. Well, that's going to be 1001 A, which is 2, plus C, which is 9, so that's 11, plus 110, 11. Because 8 plus 3 is 11. And it strikes me as odd that both of those are 11. And actually, 110, that has a multiple of 11 as well. And 1001, let's just double check, it also is a multiple of 11. Interesting. Very interesting. So it looks like in this case, I have no idea what these numbers add up to. 2882, just grabbing my calculator, 9339, total of 12221. Okay. But if I just realized I have 1001 and 110, they both have factors of 11. So what I could do is I could actually say 11, 91 A plus C plus 10 B plus D is equal to EF GF E. Okay? So that tells me no matter what my A's and C's and B's and D's are, this little fact means that my 5-digit palindrome has to be a multiple of 11. Now, multiples of 11 have a very special property. Okay? So if we think about, there are often shortcuts to telling whether a number is divisible by a certain number. So to test whether or not a number is divisible by 3, add up all the digits. And if that sum is a multiple of 3, your original number is a multiple of 3. So, for example, 18. Is 18 a multiple of 3? Well, 1 plus 8 is 9, which is a multiple of 3. So 18 must have been a multiple of 3. 19, 1 plus 9 is 10. That's not a multiple of 3. 19 must not have been a multiple of 3. So these things called divisibility rules that are nice little shortcuts where you take a look at the digits, sum or all of the digits of a number, and you can tell what it's divisible by. There is a rule for 11, and basically you sort of create an alternating sum. I'll show you what I mean right now. So, to be divisible by 11, if I have a number and I write out its digits A, B, C, D, E, F, G, H, and so on, then what we need is A minus B plus C minus D plus E minus F, yada, 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 to be divisible by 11. So, for example, 132. 1 minus 3 plus 2. Well, that's 0. That's a multiple of 11, so 132 must be divisible by 11. And in fact, this is 11 times 12. 1331. Well, we do, that's going to be 11 times 121. But we can tell it's going to be divisible by 11 because 1 minus 3 plus 3 minus 1, well, that's also 0. Let's think of one that doesn't have, 407. That's going to be 11 times 37, and that's 4 minus 0 plus 7 is 11. So, because we know, so EFGFE is a multiple of 11. Now, since EFGFE is a multiple of 11, then that means that this alternating sum, E minus F plus G minus F plus E, is divisible by 11. Okay. So I think what we could probably do is work out maybe different values for this sum. Because the E's have got to be between 1 and 9. The G has to be between 0 and 9. And the F's have to be between 0 and 9. Well, what's the biggest sum we could have here? Well, the E's and the G's could be 9, and the F's could be 0, because we take away the F's. So that's going to have to be between sum of 3 9s, 27. And what's the lowest it can be? Well, the E's could be at least 1. The G could be 0, so that way we're not adding anything. And the F's could both be 9. So 1 minus 9 plus 0 minus 9 plus 1, that's going to be negative 16. And since we know it has to be a multiple of 11, it's got to be either negative 11, 0, 11, or 22. All right. So that narrows down something. So what else can we do here? We've got possibilities for our E, F, G, F, E, that alternating sum there. But does that really get us closer to actually, because remember, we want pairs A, B, B, A and C, D, D, C that give us another palindrome. So we assumed we had A, B, and C, and D. They gave us another palindrome. We realized multiple of 11. Okay, that's fine. And it gave us this alternating sum. But is there really anything else we can do here? Let's see. In the example they gave, they had A plus C and B plus D being 11. So this is actually, no matter what, as long as A and C and B and D satisfy this, as long as A plus C add up to 11 and B plus D add up to 11, we'll still get this one out as well. So actually, we might not have needed to do all this divisibility rule stuff. So we're going to put this on hold for a moment. Okay, so as long as A plus C is equal to 11 and B plus D is equal to 11, we get this outcome. Now, we only care about pairs, right? Not ordered pairs? Yeah, there are pairs, but we don't say ordered pairs. So A, B, B, A, C, D, D, C is the same as C, D, D, C, A, B, B, A. So we only count this once, 2882 and 9339. We don't count 9339 and 2882 as a separate pair. So that should help us out a little bit. All right, so going back to the question, we'll assume we'll let A be less than C. That way we don't double count these things. So A could be 1, and then B could be 10. Well, that's not going to work. How about 2, because they have to add up to 11. 2 and 9. And then that gives us, actually gives us a whole bunch of things. 3 and 8. 4 and 7. 5 and 6. And now B and D, doesn't really matter what they are, but they have to add up to 11. So we could have 0 and 11, no, 1 and 10, no, that's not going to work. We'd have 9, 10, 2 and 9, 3 and 8, 4 and 7, 5 and 6. Now, once I have A and A and C, I can choose any B to go with the A and any D to go with the C, because I've already made sure that A, B, B, A, and C, D, D, C are only going to be counted once by saying A is less than C. So I actually have other pairs I can work with here. 6 and 5, and 7 and 4, and 8 and 3, 2 and 1. Right? So 1, 2, 3, 4, 5, 6, 7, 8. We have 4 others here, so 4 times 8 is 32 pairs. And these pairs add to 1, 2, 2, 1. 1, 2, 2, 2, 1. Sorry. So, for example, I have 2, 3, 3, 2, and then it would have to be 9, 8, 8, 9, or I could have 5, 4, 4, 5, and then the other one's got to be 6, 7, 7, 6, or I could have 2, 8, 8, 2, 9, 3, 3, 9. That's the one we're already familiar with. So we have 32 possibilities. Now let's just double check. 32, are we wildly off if we extra counted things? Well, there's B, 32. So we have 32 possibilities. We know A is already out. We have 32 of them. Could there be more possibilities, though? And that's the problem. So that's why I think I need to go back to our theoretical work. So this stuff over here as to what E, F, G, F, and E might be. E minus F plus G minus F plus E, being negative 11, 0, 11, or 22. Okay. Well, so that's 32 possibilities. So the answer might be B. There might be no more. But I'm willing to bet there's probably at least a few more, if not a whole other batch of 32 or something like that out there. What else can I do? Okay, so we know 11, and we got 91 A plus C, and then it's 10 B plus D, and we know that that's E, F, G, F. Okay. So, we know A plus C has got to be less than 18, and B plus D is also less than 18. So E, F, G, F, E is going to be less than 11 times 91 times 18, or 91 times 18 plus 10 times 18. Okay, and so what's that work out to? 91 times 18 plus 10 times 18. So it's going to be less than 11 times 18, 18. It's going to be less than or equal to 19998. And that's actually a really big clue, because that means E has to be 1. So that's really nice. E has to be 1. We can't have anything ridiculous out here. E's got to be equal to 1. Right? A and C are at most 9 because they're single digits. B and D are at most 9 because they're single digits. So we can work this out. So E's got to be equal to 1. So we're looking at our 5-digit palindrome. Has to be 1FGF1. Fantastic. Okay. Another thing that tells us, just based on that 1, that tells us that A plus C must end in 1. Right? Because if we have A, B, B, A, C, D, D, C, and we add them up, they're going to have to be 1F, GF1. Okay? So A plus C's got to be either 1 or 11. Well, we've already seen what happens when A plus C is equal to 11, as long as B plus D is also equal to 11. Okay. This is actually pretty useful. So I don't think we really need it. I mean, maybe we'll need it in a moment, but I don't think we needed all this divisibility rule stuff, so I think that was sort of a sidetrack. That's okay. Sometimes it takes a little while to work out what exactly we need to do. No shame in that. If we run out of time, that's okay. We run out of time. We've already narrowed down our guesses. We know it's definitely not A. That's a 4 out of 5 guess. If we can narrow things down just a little bit more, if we can show it's not 32, maybe it's 36, or I think 44 or 48. 36, 40, and 44, sorry. If we can show it's one of those three, we might as well take a guess. So if we can just get, at least one more palindrome that works, or a pair of palindromes that works, then we'll know it's not B, and we'll have a 1 out of 3 guess, at which point we should take it if we run out of time. Okay. Anyway, so A plus C is either 1 or 11. Now, we've already seen what happens. Now, can A plus C be 1? No, because A and C are both less than 1, or both at least 1. So A plus C is equal to 11, and this is starting to lend credence to the fact that it might be 32, because we know A plus C now has to be 11. So that's important enough that we're going to circle that. So A plus C is at least 2, so it can never be 1. So we're looking at 11. A plus C has got to be 11. Now, at this point, could maybe we figure out what F is? So we've got 11 times 91 times A plus C, which we know what that is, plus 10 times B plus C, or plus D, sorry. And that's got to be 1FGF1. Well, we know that that's 11, 91 times 11, plus 10B, plus 10 times BD plus D, is equal to 1FGF1. And 91 times 11, that is 1001. So we'll multiply that by 11. So we're left with 11011 plus 11 times 10, so 110 B plus D is equal to 1FGF1. All right. So whatever B and D are, they'll determine what F, G, and F are. And actually, if, then this is just a little side note, if B plus D is equal to 0, which there's no reason it shouldn't be, the 1FGF1 is equal to 11011, and that's another possibility. and that's 0 and 0. So there's at least another possibility. So if we took 2002, 9009, 3003, 8008, we worked out a whole bunch of possibilities for A and C on the last page. We had 2 and 9, 3 and 8, 4 and 7, 5 and 6. So here's 4 more possibilities for palindromes that add up to a 5-digit palindrome. So that brings us to a total of 36. So now we have at least 36, that's C. Maybe we'll find more and get D or E, but now we've narrowed it down to 3. So I know this is taking a little while. Maybe it shouldn't because it's only question 25 on the Pascal. But, it's taking us a little while. But we've reached a point now where if it's time's up, we can guess, and we'll expect better than if we left it blank. And that's important. Okay? But let's keep looking at it because, this is just a YouTube video. We have all the time we want. But I know that you guys should be mindful of your time when you're doing contests. Okay. So this is 4 more pairs for a total of 36 pairs. Can we have B and D be other things? Well, so what we've got here is 110 B plus D. Let's just do this carefully. That's going to be 1F G F1 minus 11011, which is actually just minus 10001 minus 1010. So I should be able to take those off. So it should be FGF0 minus 1010. And then I can divide both sides by 10. So 11 times B plus D has got to be FGF. We're dividing by 10, so we just take off these zeros. So FGF minus 101. Now 101 is not a multiple of 11. All right, we'll just double check that. Yeah, not a multiple of 11. The closest thing is 99. Is there anything else we can do here? See, what I'd like to be able to do is actually use some of my divisibility rules and say, F minus G plus F has to be divisible by 11 or something like that, but this minus 101 is really causing me a pain. So I'm going to rewrite this and think for a moment. So FGF, that could be minus 99 minus 2. We're going to bring the 99 over this side, B plus D plus 9. FGF minus 2. Okay. So now I'm actually going to break this down into 2 cases. I don't think you really need to, but no, we don't need to. So I'm trying to think if there's a way. I can't remember, which is unfortunate right now. But if I have A, B, C is divisible by 11, I know that this has got to be divisible by 11. If A, B, and C is not divisible by 11, does the remainder of this thing equal the remainder of that thing? I'm trying to remember. I think it does. Let's do a little test just to see if we can make sure. So 1, 3, 3, that should be 1 minus 3 plus 3. Well, it does give me the remainder of 1 I want. But let's try a bigger one. 1, 3, 3, 4. So that's 1 minus 3 plus 3 minus 4. That doesn't give me what I want. Okay. Really, at this point, I'm looking for palindromes that are bigger than a multiple of 11. That's ultimately what I want right now. Okay, so what can we do about this? Should I even have gone this route? I think so. I think I like where we're at. Single 3-digit number FGF. Palindrome that's got to be 2 more than a multiple of 11. Got to be only so many times that can happen. So let me think about my divisibility rule. If I have digits that look like this, dn minus 1, all the way down to d1, d0, then the way my divisibility rule works is d0, it's got to be the positive 1, d1's got to be the negative 1, d2 has got to be the negative 1, d3 has got to be negative. So I think as long as the units digit is the one that's positive, which for d3, for 3 digits, it will be. Yeah, I think the remainder when I do the sum is going to be, yeah, so that's exactly what I want. Okay. So I need FGF to have a remainder of 2 when I divide by 11. So then, so f minus g plus f must have a remainder of 2. So why does this work? Well, FGF is equal to 100F plus 10G plus F. Okay? But that's 99F plus F plus 11G minus G plus F, which is 11 times 9F plus G plus F minus G plus F. So the remainder of this thing when you divide by 11 will be the remainder of this thing when you divide by 11. Okay, fantastic. So I know 0 has got to be between, F and G are between 0 and 9. So F minus G plus F has got to be, at best, we have 2 F's are 9 and 1 G is 0, so 18. And at worst, the 2 F's are 0 and the G is 9, so negative 9. So we want all the things in here that, and we want to, if we take away 2, we want multiples of 11. So 16 and negative 11. So f minus g plus f minus 2 is negative 11, 0, or 11. This hasn't really helped us. Okay. That's fine. Let's take a look at what we've done. Maybe that'll give us a bit of inspiration here. So we had this nice 1, 1, 0, 1, 1. And when b and d added up to 0, we were home free. Now we've got this 1fg f1. So we know that e had to be 1. There was a nice way to work that out. Could we have... Actually, I think we could probably limit what f is the same way we limited what e was. So we're going to ignore all this again. And I know that 110 b plus d has got to be fg f0 minus 110. Okay? But b plus d is less than or equal to 18. So what's 18 times 11? So we're going to have 1980 has got to be equal to fg f0 minus 1010. Adding 1010 to the other side, we get 2990 is equal to fg f0. So we have less than or equal bars here. So f is at most 2. Okay, so once again, didn't need to do a whole bunch of work. F is at most 2. And that actually narrows things down rather nicely for us. So we can take a look at f at 0. We could take a look at f is 1. And we could take a look at f is 2. Right, and see what possible values we can get here. So I'm going to use this 11 times b plus d is equal to 2 is equal to fgf minus 101, but that's going to be some numbers here. So 11 times b plus d is equal to fgf minus 101. But in that case, that's just g0 minus 101. So we have no solutions here because b and d are both non-negative. So this side will be non-negative, but g has got to be at most 90, so this is at least negative 11. Not going to work out. Not going to work out at all. That's okay. How about if f is 1? Well, we got 1g1 minus 101. And once again, I can get g0. So I'm looking for g0, so 0 is between, 0 is less than g is less than or equal to 9. So g0 is going to be between 0 and 90. So multiple of 10, that's also a multiple of 11. Going to have to be 0. That tells me g is 0. And in which case we have, well, we'll deal with that. We'll deal with that right now. So what I'm noticing is I really shouldn't have been using any of my divisibility rule stuff at all. I don't think that has helped one bit. So sometimes you can know a little too much math. So right now, EFGFE has got to be 11011. And we have dealt with all those cases. Because we did that back here, that was the case when b plus d is equal to 0. We got all those 4. So I'll just make a little note. Gave 4 pairs we accounted for. Okay. How about f is equal to 2? Well, that means 11b plus d is equal to 2g2 minus 101. And that's going to have to be 1g1. So, looking for multiples of 11. We have 101, that's not a multiple of 111, 121, 131, 141, 151, 161, 171, 181, and 191. There should really only be one of these in here that is a multiple of 11. It's this one. None of the others are multiples of 11. So 1g1 has got to be 121, and that means g has got to be 2. And that means EFGFE is equal to 12221. Well, we did a bunch of those with 12221, but we did them by taking a look at saying, oh, they gave us 2882 and 9339. What other possibilities can we get? So we got a whole bunch, but we didn't necessarily exhaust that list. Okay? But we can see in just a moment that we must have exhausted that list, because we already know a plus c has got to be 11. Well, if 11b plus d is equal to 121, therefore b plus d is equal to 11. That was 32 possibilities. And that we already saw. So actually, we've already worked out all the possible ones that we've got. And there were 36 possibilities. I'm not going to list them all out again. I actually didn't even list all of them out in the first place. But we know we want C36. Okay? Just double checking. Yep, C36. Okay? And just a little bit of a note. I mean, this one did take us a while, or it took me a while. It might have not taken you very long at all. Anyway, so I noticed this was taking a while, so I finally said, aha, I got 4 more, so I know the answer is at least 36. At this point, I know it's 36, 40, or 44. I can take a guess. Keep working on the problem at that point, unless you have another question, an easier question that you might be able to solve in the meantime. But if it comes down to it and you run out of time and you have to guess, you have to use your intuition. Now, we know that there are at least 36. There might be more, but we don't know. So in that instance, I would say, guess 36. Unless you've been doing a whole bunch of work, and you think you might be close to an answer and there might be more, in which case don't guess 36, guess either 40 or 44. Because if your intuition is right, now you've actually narrowed it down to 1 out of 2 possibilities. Okay? So we shouldn't guess if we ever can help it. But I know that you're only allowed 1 hour on this thing. So if you have to guess, be smart about your guessing. At one point, we knew there were at least 36, so 36 was a safe guess. But if we did a little extra work and it looked like there might have been more, turns out there wasn't, but if it had looked like there might have been more, and the proctor says, a minute till pencil's down, guess one of the ones that are more. Guess where your intuition is going. Okay? But we got our answer of 36, and that completely finishes off the 2001 Pascal. Thank you guys for watching, and I guess I'll move into a 2001 Cayley or a 2002 Pascal next. So stay tuned for those videos, and yeah, that's about it. So thanks for watching.